So this is our summary of energy. So again, these are the different types of energy. When we talk about energy, we're going to use this unit here, the joule. So this was named after a physicist who studied a lot about energy. So they named the unit after him, J. Just like we had Newton's N, here we have joules, J. Okay, so let's talk about kinetic energy. So it takes energy to get objects to move. So for example, here, when we have this fighter jet, so jets that take off of planes, they have a really short runway. So they need to get to a really quick speed in order to take flight in not a long amount of time. So for example, it takes a huge amount of energy to get them to move at 170 miles per hour in about 2 seconds. So 0 to 170 in 2 seconds is an insane acceleration, right? So this is something that takes a lot of energy to do. And we can see that here, right? We can see all the energy from all of the gas that's being shot out the back of this. So what we call this energy, is often thought, kinetic energy is often thought as the energy of motion because it describes energy, objects that are moving. So we say this jet here has a lot of kinetic energy because it's moving very quickly. So kinetic energy depends on the speed and the mass of the object. So if we're increasing kinetic energy, we can change the speed or the mass. So kinetic energy is the simplest. We can think of objects that move have kinetic energy. All right, potential energy is kind of interesting because potential energy can kind of be split into a lot of different categories. We're going to focus on one type, but I want to show you all the different types. And we'll look at some videos and clips to kind of help us understand what's going on. So this went with our warm-up question yesterday. Yesterday, I asked you guys where a roller coaster has more energies. It could be at the top of the hill or the bottom of the hill. And we're kind of split between the two. But a lot of you said towards the top of the hill, it had a lot of energy. And this is where we're talking about with potential energy. So this diver is going to jump from the end of the diving board. After she dives down and is falling into the water, she'll have kinetic energy or energy of moving matter, right? So right now, she's still, but before she hits that water, she's going to be traveling really fast. But even if she's momentarily stopped high above the water, she has energy. So the idea is the energy has to come from somewhere, right? So the energy is coming from the fact that she's so high up. That's what we call stored energy. So the diver has energy because of her position high above the pool. This type of energy is called potential energy. So potential energy is the energy that's stored in a person or object. Often the person or object has potential energy because of its position or its shape. So that's kind of our, if we think of kinetic energy is objects that are moving. Potential energy is because of position or shape. So how high they are up from the ground and what they're made up of. So we're going to look at a couple of those together. All right, so types of potential energy. So these slingshots, right? We think of the shape or what it's made up of here. Energy that we can release for motion, for movement. Springs, we can push down on a spring and we can get them to store energy. So if we push this down, it will, once it comes, bounce back. So this is what we call elastic potential energy. So from stretching or compressing. Our next type of potential energy is what we call electromagnetic. So this is actually pretty cool. This is caused by magnets or opposite charges. So we know that, or sure, it should be the same. Or actually, that's fine. It could be opposite, it could be the same. Either one's fine. So let's go and take a look. We have a couple different clips that show this movement here. So we can see all of these are made up of magnets. So here we can see we have potential energy from the magnets being transformed into kinetic energy, the moving of this ball. There are weapons that are called railguns that kind of work the same way. They used to be science fiction, but we actually have real ones where if you imagine you put a bullet here and you accelerate it through a track with magnets. There's also trains that work this way, the maglev trains. So there are trains that kind of float on a series of magnets that are pushed forward due to these. So if you've ever been, there's some roller coasters work this way too, where they just have a bunch of magnets, they let go and it takes off. And this is good because there's no movement parts. So there's a lot less friction going on here because the magnets aren't touching the ball bearing. Cool. So that would be another type of potential energy. So this is made up of the shape or what the objects are made up of. Our last couple types, so here we have chemical potential energy. So here we have a propane tank. So there's energy that's stored inside this propane tank. And we know that because we can use it to create fire or do other things, but all this energy can be released. And we can see this in the form of heat, of moving gases. So these gases start moving. So we have kinetic energy, we have heat, we have a lot of other things until finally we can get a massive explosion that shoots off materials in all which ways. Let's see, where's a good shot? So you can see here, some of these objects are given a lot of kinetic energy as they're pushed out. So that flying off to the side is an example of another set of potential energy. So it can be stored in bonds. So these ones, we're not doing too many calculations with them, but they are energy. So if you knew how much energy was given off, you can use this to figure out how fast something's going to move or a couple other things. So what we're going to focus on mostly is our what we call gravitational potential energy. So this is energy caused by gravity. One of the best ways to think of it is things that drop, right? So if we have these drop rides, you're taken all the way to the top where you're not moving at start, and then gravity is going to speed you up as you rush towards the ground. So this is what we call gravitational potential energy. So what we're going to do is we're going to write down a couple equations. So we're going to just do this on a sheet of paper because it's a little bit easier than having to type all of this out. So we're going to look at a couple major equations today. So we're going to kind of define what all of the variables are because some of them are the same on both of them. And then we will look at what the equations are. So we're going to abbreviate kinetic energy as KE. And we're going to abbreviate potential energy as PE. So our equation for kinetic energy is going to be equal to 1/2 mv squared. Or you could say KE is equal to 0.5 times mv squared. You don't want to deal with the fraction. This is the same thing as a decimal. So either of these are fine. And we've seen these values before. M is going to be our mass in kilograms, and V is going to be our velocity in meters per second. Since the velocity is getting squared, it doesn't really matter if it's positive or negative, because if we have a negative velocity, our answer is going to be positive, because negative times negative would always give us a positive. So our kinetic energy is always going to be our, so we have KE is our kinetic energy. And we use J to represent joules. So our unit would be joules. So that's pretty simple. We have mass 1/2 or 0.5 times mass times velocity squared, or 1/2 mv squared is how we say it. Our potential energy is going to be equal to the, this is based off velocity, right, or speed. Potential energy is based off position. So our formula is going to be mgh. So M again is our mass in kilograms. G is our acceleration of gravity. So it's 9.8 meters per second squared. So G is always equal to this for all of our problems. And then H is our height. In units of meters. So these are our two equations. We're going to use these to find kinetic energy and potential energy for a couple different problems. But the calculations themselves are going to be pretty simple. So for today, we're going to focus on plugging into these equations, and then we'll start connecting them together later on this week. So I'll leave that up for you guys in case you need to still get it copied down, and we'll move on in just a minute. Okay. So let's go ahead and look at a couple questions today. All of ours are going to be pretty simple. We're going to be using one of these two equations. So here we have one question, example number one. This is the first one we're going to do. You serve a volleyball with a mass of 2.1 kilograms. The ball leaves your hand with a speed of 30 meters per second. So for example 1, we're given the mass, 2.1 kilograms, and the speed. So speed, we can say, is going to be the same as our velocity. We'll just say that it's moving forward, so we'll put it as positive. So our question for this one, right? What kind of energy do we have if we're talking about a volleyball that's traveling with a certain speed? Are we going to be measuring the kinetic or potential? So we got 1 guess in, and that's correct. So if we're given a speed, we're looking at a kinetic energy. So the type of energy that we have is kinetic energy. Because our ball is moving. So we can fill in our type of energy is going to be kinetic energy. So looking at all the info that we took from our slide, let's kind of look at what we're doing here. So we have kinetic energy because our ball is moving. We know that the mass of the ball is 2.1 kilograms and the velocity is going to be 30 meters per second. So looking back at our equations, we know that we have, go and move away. We're going to use our equation here with kinetic energy. We have our mass and velocity. So we can say that kinetic energy is going to be equal to 1/2 mv squared. So we're just going to plug it in. Times 2.1 times our v, which is 30 squared. So if we square this 30 times 30, we should get 900. So let me get my calculator out so we can go through this. So we square 30 squared will give us 900. So put that down. And from here, we're just gonna work it out in steps. So from here, we can do 2.1 times 900. And when we multiply by 1/2, you could do this 2 different ways. You could multiply times 1 divided by 2. So multiply by 1/2. Or you could just do this divided by 2, because if we multiply by 1, it's not going to change the value. So we should get a kinetic energy of 945 joules is our answer. So that's how we would go about a question like problem number 1. We're given velocity, so we know that the ball is moving so that we can find the kinetic energy. And we plug in with this equation here. So let's look at our second example and see how we deal with another type of energy. Actually, why don't we, oops, I got the 2 switched up. Why don't we skip, instead of doing example 2, let's do problem number 1 so we can see the other type of problem. So we're going to skip example number 2. We'll have you guys try that on your own. That way we get to see the other type of problem here. So again, we're just gonna have you work on this one, and we're gonna switch the order of these. That way we get to see both types of problems. All right, so problem number one, we have a cinder block sitting on a platform that's 20 meters high and weighs 7.9 kilograms. So this block is just sitting there, it's not moving, but we know it has energy, right? This block has the potential to do some real damage. If it's to fall off a 20 meter, so that's gonna be about 20 meters, it's 1.6. So it's probably like a 2-3 story building. It's gonna do some damage. That cinder block's gonna be falling pretty fast when it hits the ground. So we know that there's energy stored just because it's so high up. So that type of energy is gonna be our potential energy. So here we have potential energy. We know that because it's 20 meters off the ground. So that's kind of our key, our clue. So here we're given two different things. We know that we have the height, which is h, is 20 meters, and it weighs 7.9 kilograms. So 7.9 kilograms is our mass. So this is going to be all the information that we need here, going with problem number one. So we know it's potential energy because it has some height, 20 meters off the ground. It has some mass, m. So we're going to plug into our equation, potential energy equals mgh. So our potential energies are mass, 7.9, times g, and g wasn't given to us in the problem. G is always going to be 9.8 meters per second squared. So this is a constant, it never changes. So anytime we're dealing with the potential energy of something, the gravitational one, based off of gravity, we're going to use this here. So one question, right? We're always going to use 9.8 meters per second for all the problems that we're dealing with. When would we use a different acceleration of gravity? So when would we use a different number for this? On a different planet, yeah, right, you're absolutely right. On a different planet, it's going to have different accelerations of gravity. So say on the moon, stuff's going to have a lot less potential energy because it's going to get pulled down a lot slower. So if I have like this brick sitting on 20 meters off the ground on the moon, it's going to have a lot less energy. Yeah, awesome. Okay, so we know that we have our mass here is going to be 20 meters. Sorry, our height is 20 meters. So we just plug it in. So potential energy is going to be equal to our mass times acceleration of gravity times our height. So mgh. So we have 7.9 times 9.8 times 20. So we're going to get 1,548.4 joules is our answer. So we can see that brick that is on a tall building has more energy than a softball that's moving pretty fast. It's just this energy hasn't been translated into motion yet. So this is the energy that's stored in it. Kinetic energy is like one way that we can release the energy. Awesome. So we jumped around a little bit. So we had example number 1 and problem number 1 finished. So what we're going to have you guys do for the rest of the period today is we're going to have a chance to work on the rest of these. So we have, we're going to have you go back and do example 2 here, and then finish problems 2, 3, 4, and 5. So I'm going to let you guys get started with that. And we'll have a chance to go over any questions you may have about stuff from yesterday as well. So I'm going to go ahead and set it up so that you guys can go and get started with that. Yeah, so you can do problem number 2, example 2, before you do the rest of the problems. It's just going to be more practice for you guys.